guys, this is our first training about FPGAs. My name is Leonardo. I'm going to show you how to use FPGAs from Xilinx, and we're going to focus now in the Verilog language, okay? We're going to do some labs with the Spartan 3 board, okay? And with the Zeboard. Also, in order to program our FPGA, we're going to use a JTAG cable, okay, this one here. It's more than enough. The format of the training will be like this. I'm going to show you some introduction, then we're going to switch to the board, and after the board, I'm going to show on the screen what to do, how to use the software in order to program the FPGAs. Hope you guys enjoyed, and any doubts or other questions, and also if you guys want me to talk more about some subject, please add a comment and then let me know, okay? See you soon. So let's start. What is an FPGA? FPGA stands for Field-programmable Gate Array, which means is a chip that you can program it like your normal microcontroller would do, but with some differences that you're going to see on the future, okay? What they can do? Basically, the FPGAs can do any computable problem. It's a normal Turing machine. There is no such a thing that a microprocessor can do and an FPGA could not. By the way, you can even do a microprocessor inside the FPGA. So there is really no limit on what you can do with the FPGAs, okay? And why we use them? FPGAs are fast and flexible. For instance, it's possible to change the programming of the FPGA on the fly while it's already in your customer without a need to do a recall. What are the use cases in FPGAs? Okay? Normally people use a lot of FPGAs to do a ZIG prototyping, which means before you produce a chip you need to test it, and normally is where you use FPGAs. Okay? Also, a lot of people now use FPGAs for algorithm acceleration. Imagine that you have in your board a microprocessor and an FPGA, and for instance all the heavy lifting is done in the FPGA, all the other part of the logic like graphical interface or something else that does not need to be really real time, you can do on a microprocessor. Okay guys, let's start by showing you guys what we have in an FPGA. As shown before, an FPGA is just a simple chip with a lot of IOs, okay? And what you have inside those guys? You have logical cells, okay? The logical cell is the core of any digital function that you can have in an FPGA, okay? Inside a logical cell you can have a lookup table, a flip-flop and a mux. Only with this block, any combination and sequential logical could be done, okay? Between the logical cells you have interconnects, okay, which are programmable wires, okay, that are going to implement the digital function that you want to create, okay. You have block RAMs. Block RAMs are a specialized part of the FPGA that can be used only to create RAMs. This is really useful because sometimes you want to implement RAMs and you don't want to burn your logical cells to do that. You have specialized DSP blocks. Normally inside these DSP blocks you have a 48-bit multiplier and followed by an accumulator. Okay? With those blocks, any digital filter can be created with a very high throughput. You have DCM blocks. This DCM blocks comes from Digital Clock Manager and is used, for instance, to synthesize new frequencies or fix a duty cycle, and we're going to see this later. The last part is the I/O block. The I/O block here is where you can configure, for instance, which voltage level your I/O is going to have. Okay, and that's it, guys. This is more or less what we have inside an FPGA. The next part I'm going to give you a quick review on digital gates before we change to the lab. Guys, let's talk a little bit about the logic functions, okay? We have basically 4 more important logical functions, okay? The NOT, AND, OR, and XOR. Okay, let's talk a little bit about each one of them. The NOT gate. The NOT is simply a guy who is going to invert the input. For instance, if the input is 1, the output will be 0. If the input is 0, the output will be 1. Here you can see this in our truth table. Okay? If E is 0, output 1. If E is 1, output will be 0. The next one is the AND gate. The AND gate will output 1 only if all his inputs are 1. Okay? For instance, here, if A and B are 1, you're going to have 1 at the output. The OR gate. The OR gate is going to be 1 each if at least one of its inputs are 1. Here, if in those cases, if B is 1, A is 1, or both are 1, C is going to be 1. The XOR or exclusive OR is a little bit different. It's going to output 1 only if one of its input is 1. Okay, here in this case, if only one of the inputs are 1, the output will be 1. All other cases is going to be 0. Now we're going to talk a little bit about the universal gate, the NAND gate. Okay, the NAND gate is in theory the same thing as the AND gate with the addition of an inverter. Okay, why the NAND gate is so important? First of all, with an AND gate you can implement all the other logical functions. I mean, with an AND gate you can do a NOT, OR, AND, SHOR, and XOR. We're going to see a little bit how to implement them in some lesson. Okay. In the truth table, we can see that the NAND gate has exactly the same result as an AND, but inverted. Okay? For instance, if we want to create a NOT with an AND, what we could do? If you just this, for instance, is an inverter. Okay? Yes. As I showed before, with the NAND gate, you can create all the other logical functions. For instance, if you want to create a NOT gate, you just short the two inputs and you have a NOT. If you want to create an AND gate, you just invert the output of the NAND. This is quite simple. If you do this, if you invert and invert again, is basically an AND gate. An OR, what you can do, you just invert every input, okay, and this result we send again to an AND gate. This also can be known as the De Morgan theorem. Okay. The XOR is a little bit more complicated and is implemented like this. Okay. So, in resume, why the NAND gates are so important? Basically, because they can easily be implemented with CMOS, okay? And with a simple NAND gate, all the other logical functions can be created. Now that we talk about the logical gates, let's talk a little bit about the digital circuits, okay? Actually, we have just two types of digital circuits. Sequential digital circuits and combinational digital circuits, okay? The combination of circuits has no memory, which means, for instance, this circuit here, if A or B or C changes, D will change immediately. There is no memory, okay? The D will change as a function of A, B, and C, disregarding of time. Now sequential circuits. Sequential circuits have memory, okay? Kind of sequential circuits are ROMs, state machines, registers, counters, or FIFOs, okay? For instance, here is the simple case of a flip-flop D. The flip-flop D is going to sample the input only in the rising edge of the clock. If the rising edge does not come again, the previous input will be memorized forever. So this is, for instance, the simple case of a 1-bit RAM, a 1-bit memory. Okay? Before we continue, let's talk a little bit about the FPGA workflow. Okay? The first point, we write some HDL code. We describe the hardware that we're going to generate. The second point, we test what we just write. Okay? The third point, we synthesize our hardware, which means we're going to create a file called netlist from the logic that you want to create. The fourth point, we're going to map the netlist onto the FPGA resources. The fifth point, we're going to generate a bitmap file from the mapped netlist. This is called a bitstream. Okay? The sixth point, we're going to program our FPGA using a JTAG cable, normally, for instance, one like this. Okay, now let's go to our labs, guys. In our first video, we're going to create two labs, okay? One lab for a combinational circuit, okay, with this digital function, and the other lab, a simple flip-flop D, okay? The software that we are going to use is going to be Vivado, okay? And we are going to use two interesting features: the integrated logic analyzer and the virtual input-output. We're going to show how we can drive our FPGA board remotely through our JTAG cable. Okay? So, see you guys in our lab. Okay, go to File, New Project, and create an empty project. Then, we just choose the Zeboard. In this lab, we are not going to write our circuit in Verilog or VHDL. We are going to create a new block design, and we are going to choose the IP that are going to implement the AND and the OR function that we need to our lab. Here we just click Add IP, type logic just to filter out the IP that we want. If you click twice, you can choose the function that you are going to implement. Here is the AND one. Here we just configure the size. Okay? Now we just copy and paste this block to create our OR function. At this point, we are going to connect the output of the AND to one input of the OR, and we are going to put the ports, the external ports that are going to drive our circuit. Now, just to clarify a little bit, we change the name of the ports. Here, we just add in the last port, and we're going to change the name to A, B, C, and D. After the block diagram is done, we can create the HDL wrapper, which is going to generate a Verilog or VHDL code that are going to instantiate our block diagram. Now, to really connect our circuit ports to our FPGA pins, we need to create a constraint file. In the constraint file, we're going to lock the pins to the ports in our HDL code, and also we're going to define the voltage level of our ports. Regarding the voltage levels, we need to take a reference in the user manual of the Zeboard or the board that you are going to do. To help comprehend this, I'm putting the picture of the real board at your left. Okay? The switches are going to be mapped to the port A, B, and C, and the LED is going to be mapped to the port D in our project. We are not obliged, but we can add multiple blocks in a subsystem just by clicking and put create hierarchy. Now that everything is done, we create our bitstream file. This can take a little bit long to complete. We are just going to jump, okay? And after the bitstream is complete, we can program through our JTAG cable the FPGA board. This is the result of the first lab. As you can see, here we have the inputs A, B, and C. And our logic was if A and B are true or C is true, then D is going to be on. Okay, so let's just put C high. As you can see, the output go high. Now let's put A and B high. Again, the output go high. So nice job, the lab is working. Okay, now let's start our second lab. Just to remember, the second lab will be a flip-flop D, okay? Now we just create an empty project that we point out to the Zeboard. And in this example, we are going to write Verilog code to infer our flip-flop D. Just to remember, the flip-flop D is going to be a 1-bit memory that are going to memorize the input D at the rising edge of the clock. In this example, we are also adding a asynchronous reset, which means at every point that the reset goes high, the output of the flip-flop are going to be 0. Okay, let's start. In this case, that we are going to infer a sequential circuit, we are going to use the construct always. Okay, the always block is you can imagine as a piece of code that are going to be executed if the sensitivity list, which is something that is inside the parentheses, become true. In our case of the flip-flop D, the always block is going to be executed in the rising edge of our clock and also in the rising edge of our reset. So if clock goes high or reset goes high, the content of the always block is going to be executed. Here we just type that if reset is 1, the output of the flip-flop is going to be 0, or else in the positive edge of the clock we're going to sample the input D and pass to the output Q. Okay? Here we are creating a variable of the type reg called Q because the always block always need to output its value to a reg variable. Just attention, reg here can mean register, but this does not mean that reg is always going to be implemented as a register. We are going to see in the future that the always block can also use to create combinational circuits. So in this case, the reg there is not going to be a register. Now again, let's add our constraint file. Okay, this part we can just copy and paste for the previous lab and change just the signals because it's more or less the same. Just one detail that you're going to show in the, here in the next seconds is that as we are using here a signal that is going to be the clock, by default the synthesizer will complain saying that you're using a pin that's not specialized for the clock. But in this case we are going to use a command that you're going to say to the synthesizer that you don't care, you really want to use this pin as a clock. Okay. In this case here, we just forget to change our always block to also add the pose edge to the reset port. Now let's compile or synthesize our code, which means we are going to ask the synthesizer to create a piece of hardware that implements the code that we write in Verilog. Okay, here we just opening up the circuit that has been implemented by our synthesizer, just to take a look and show you guys that it's a really flip-flop. Okay, and after this step we are ready to go. We are going to implement and then generate the bit stream. Okay guys, now let's switch to the board and see if everything is working fine. So, as we did in our second lab, this pin here, this switch is going to be the D part, the input of the flip-flop D. Here will be the clock and here will be the reset signal. Okay? If you want to latch our input, we can make it on, do a clock rising edge, okay, and at this point you can see that the output of the flip-flop went to high. Okay, now independent if the clock goes low, okay, or if we change the input of the flip-flop, the output will still be memorized. Okay, the only detail is that we have an asynchronous reset, so at any state if the reset goes high, our output is going to go low. Okay, the same thing for the low. If we now go to the rising edge of the clock and our input D is low, our output is going to be low. Okay, so lab 2 is done. See you guys in the next video.